This week we're starting chapter 13, which looks at the relationships among variables, and we're going to focus primarily on contingency tables this week. So a contingency table shows the frequency or relative frequency of each value of a dependent variable for each value of an independent variable. And there are various measures of association that are statistics we can calculate that measure the strength of that relationship. We're going to only focus on the chi-square statistic. Your book mentions some other measures of association, but we're going to just work with the chi-square. So let's take an example from your book. This is table 13.1, and it shows support for city-county consolidation by residents. So in other words, do the respondents to the survey reside in the city or outside the city? And the analysts want to display how the residents inside the large city and outside the city differ in their responses. And we do see some differences here if we look. Looks to be a higher support for consolidation from residents within the city than those outside of the city. By convention, the values of the independent variable head the columns, and the dependent variable are the rows. Notice the values for support for consolidation are arranged in this order: for, no opinion, and against. Column percentages add up to 100 or close to 100. Notice a higher percentage of residents, again responding within the city, support the consolidation when compared with residents outside of the city. The joint distribution of the two variables is what we call a bivariate distribution, bi meaning two and variate meaning variables. So the city and county residents were surveyed about their evaluation of local government services and whether or not they favor the city and county consolidation. The implied hypothesis was that the support for city-county consolidation is directly related to how they evaluate their local services. And so now if we look at their support for the local services overall, in this particular table here, again the independent variables on the columns and the dependent down in the rows, and we look at across the four and we see that the percentages are dropping. So for those that have excellent or good services are more likely to be in favor of consolidation. And the opposite is true in the against column. So again, if you look across here, row rather, dropping off and this going up. The data support the hypothesis. The higher the rating for the services, the more likely the residents are to favor consolidation. And we could use a test of statistical significance to determine if the distribution in the table was likely to occur by chance. We can also include a third variable in the analysis, determine if it influences the relationships between the other two variables. In our example prior, we used resident as a control variable. So here's how the table looks when we add that control variable on top. We see a different pattern of response within each group. City residents are more likely to support consolidation if they rate the services as good. Non-residents less likely to support consolidation if they rate the services as good. So a little picture of what a control variable does. So it influences both the answers here and also the evaluation of the services. Tables are also described by their size and their dimensions. So the size is identified as the number of rows and the number of columns. Remember, the rows are the categories of the dependent and the column are the number of categories of the independent variable. And dimension is the number of variables whose joint distribution is displayed. A table showing the joint distribution of 2 would be a two-dimensional. If there were 3 variables shown, it would be a three-dimensional. Let's just talk a little bit about the kind of relationships that you might see. A perfect relationship means the change in the independent is always associated with the change in the dependent. It could be increasing or decreasing. A null means that change in the dependent is as likely to coincide with an increase or a decrease in the change in, or no change in the dependent variable. So here's an example of a perfect direct relationship. Notice as the length of employment of the program increases, the placement rate increases. A very profound, direct, perfect relationship. There's an inverse relationship. Notice here as the length of the job training increases, the placement rate decreases. And here's a null relationship. Notice as the length of the job training program increases, the placement rate remains the same. We don't see any differences, so there seems to be no association between placement rates and length of the job training program. A strong relationship will depend on the research question and some factors known to influence dependent variables. Factors affecting some dependent are well known. With a well-studied dependent, even moderate relationships may be of limited value, since stronger relationships may have already been identified and explained. With a weak dependent variable that is not well studied, even relatively weak relationships could suggest research questions worth pursuing. You can also have a nonlinear relationship. Notice the linear relationship. Employees with least working knowledge are most likely to rate human resources as poor. Least working knowledge, so in other words, less than a month. Employees with 2 to 5 years are most likely to rate as good, and then those that are there more than, actually this should be saying months rather than years here, are likely to rate as satisfactory. So in summary, contingency tables illustrate relationships between or among variables. The relationships can be strong, moderate, null, or nonlinear.